Our topic for today is about something that is also very, very important in chemistry. Although to a layman, it is just ordinary observation, and some don't think they have anything to forestall that or to mitigate it. But to a chemist, they are not ordinary reactions, especially as the waste materials and also the post threat to the living of human being. It is on this note I welcome you to this new edition of ScoreBooster lecture in chemistry. Our topic for today is going to be on oxidation reduction, and our presenter is our regular man, Said Latif. But before we go, let us try to get a scope of what we want to do today. The first thing is to identify all those ways in which oxidation and reduction reactions are represented. How do we know them if we see them? Because as I said earlier on, to a layman, they are just ordinary occurrence that to them it seems not to have solutions. But as a scientist, as a chemist in particular, it is not every time that this reaction, whether oxidation or reduction, are desirable. If they are desirable, fine. How can we improve that? If they are not desirable, how can we forestall it from occurring in the first place? Or if it has occurred, how can we limit it? So that is why chemists need to identify ways of expressing these oxidation and reductions, identifying them, and have ways of correcting them if they have happened. And again, since chemistry is a course on chemical reactions, we should be able to classify this broad reaction, oxidation and reduction, into either oxidation and reduction, because it's a very broad aspect of chemical reaction. And again, we need to balance those redox reactions, since we have taught ourselves how to balance ordinary chemical reactions in terms of atoms and molecules. So in terms of electrons and other thing involved in oxidation reduction, so a chemist should be able to balance all those things. Like I said, oxidation and reduction are very broad type of reaction. In the last lecture, we talked about exothermic and endothermic reaction. That is type of reaction in when we are considering heat content. But this has nothing to do with heat content. We have decomposition, neutralization, precipitation, double decomposition, displacement, even replacement, then oxidation. And out of all these reactions that I've mentioned, it is only oxidation and reduction that is very large. In fact, each of all these aforementioned reactions can be broadly grouped into two types: reduction or oxidation. We are going to see that one later in this lecture, inshallah. So this picture that we are seeing in front of us, the first one is the magnesium burning in oxygen. You can see that very illuminated flame. So it is the addition of oxygen to magnesium that makes it burn like that. So it's a type of oxidation reaction. This image on the right hand side is the bicycle. I believe every one of us know that if a bicycle or anything like metal is kept in a place without working, without doing anything for a very long time, rain beat it, sun beat it, everything happens like that. So later we are going to see something like this. We call it rusting. Rusting is a general name, although it's scientific, but it's general name. But to a chemist, that rusting is called oxidation reaction, because as we are going to see later, oxidation is what causes iron to be converted to iron oxide with the help of oxygen and water. That is oxidation. So this has a very big application in industry, especially in steel manufacturing industry. This is where iron 3 is extracted from the earth crust. Before iron can be used for everything they are used for, it has to be converted to a pure iron. So this picture is what represents that in furnace, in industries, in steel industry. That is where you can see the man that is operating it. So this is the iron that is being reduced to pure iron. We are going to see how it is being reduced with the grace of God now. So the first one, because in our learning objective we said we need to identify ways of classifying these reactions. So to do that, we are visiting the first one, which is in terms of oxygen. How do we define oxidation reduction in terms of oxygen? Oxidation, at least we can see from that name, oxy is from oxygen. So oxidation is a process where oxygen is added to a substance. That is oxidation. If you have a metal, oxygen is added, that is oxidation. If you have even a non-metal, the oxygen is added, that is oxidation. So the opposite, the directly opposite reaction is the reduction. That is when oxygen is lost from that substance. If there is a way of removing oxygen, like the image we just showed ourselves now from the steel industry, steel manufacturing industry, that is reduction. We are removing oxygen. So anywhere you see oxygen that is being added to a substance, that is called oxidation. Anywhere oxygen is lost, is removed from a substance, that is called reduction. So example is this: we have a pure magnesium now, and oxygen is added. In the first image that we showed ourselves, where magnesium was burning in a flame to get that white flame. So that is oxidation to form magnesium oxide. Reduction is when we have copper oxide or iron oxide or magnesium oxide. So we now pass hydrogen to it, especially this hydrogen. This copper oxide is very suitable because hydrogen is above copper in the electrochemical series. So it is easy for hydrogen to replace copper or to displace copper. So as I've said earlier, we have this replacement reaction, we have displacement reaction. So this reaction is a displacement reaction, but strictly speaking, it's a reduction because hydrogen is reducing copper oxide to ordinary copper. So there's loss of oxygen from copper oxide to ordinary copper. That is what is called reduction in terms of oxygen. So what we're trying to say in effect is that if we have a reaction and we're able to spot that oxidation has taken place, then automatically reduction has also taken place, because they go in line with each other. If a substance removes oxygen from another substance, we said that is reduction. But what about the other substance that gain that oxygen? Or the oxygen will just go like that? No, that is also called oxidation. So later we are going to see how to define oxidation in terms of each of the compounds, each of the reactants making up the reaction. You can see this magnesium now gain oxygen. Magnesium has oxidized itself, it's magnesium oxide. But what about oxygen? It has reduced itself to oxide of magnesium. So this reaction now, hydrogen has reduced copper, but hydrogen itself has oxidized because it has gained oxygen. This one has gained oxygen, it has oxidized, but oxygen has gained cation, so it has reduced. So the same thing here. So that is what we are trying to say, that we can't have oxidation without having reduction accompanying it. Another one is in terms of hydrogen. Since in terms of oxygen we have defined oxidation and reduction, so let us go to in terms of hydrogen. How do we define that? In this case now, we have added hydrogen to sodium. What does it become? It becomes sodium hydride. What is the meaning? Since hydrogen has been added to sodium has been reduced. If sodium has been reduced, then what happened to the other one? So it has been oxidized. So in that case, so oxidation is just that process where you have removal of oxygen and hydrogen rather, while reduction is the removal, is the reduction is the addition of hydrogen. So now we can combine those two definitions together, this one and the earlier one in terms of oxygen. The oxidation can be defined as a process of oxygen gain or loss of hydrogen. So reduction is oxygen loss or gain of hydrogen. So any substance that loses oxygen or that gain hydrogen, that is said to be reduced, to have been reduced. The same thing if any substance gain oxygen or loses hydrogen, it has been oxidized. That is what we are trying to say. So there are many reactions that involves oxygen or hydrogen. So it is very easy for us to define oxidation or to locate, to identify which of the reactant has been oxidized or which one has been reduced. So if this one involves some detail of chemistry, thank God we have talked about electronic configuration before. At least the first 20 elements, their electronic configuration is, we have learned them by heart now. So we should be able, having known the number of protons in a particular element, or better still, the number of electrons in a particular element or ion, we should be able to write the electronic configuration. So when we are dealing with reaction of all those elements with another, we should be able to know from our knowledge of chemical bonding, we have talked about that also, which one transfers electron, which one gain that electron. So we now attach that one to this concept now, so as to enable us to define what is called oxidation, what is called reduction in terms of electron transfer. So I go back to that reaction where we use magnesium and oxygen that we discussed here now, that we say is oxidation. So we want to define that in terms of electron transfer to prove that it is actually oxidation. Before the reaction, this is the electronic configuration of magnesium. So it has 12 electrons, oxygen has 8. So after the reaction, we know that this magnesium it is easy for magnesium to transfer that electron to oxygen. Oxygen will gain those 2 electrons. So magnesium becomes this completely filled shell, oxygen becomes this completely filled shell. And we know that if oxygen is added to magnesium, magnesium is oxidized. Having known that one, then in this case magnesium has lost that electron. Then what is oxidation now? I believe you agree with me that oxidation will now be properly defined as a process of electron loss, while reduction is process of electron gain. Let me repeat. We have established before that in a reaction between magnesium and oxygen, magnesium oxidizes. That is when we say process of oxygen gain is oxidation. So in this case, term of electron transfer now, since we have established and we have agreed that magnesium oxidizes when it reacts with oxygen. So in this case, in terms of electron, so since magnesium also transfers electron to oxygen, magnesium has lost its 2 outermost electrons. Then magnesium has been oxidized. So oxidation is the process of electron loss, while reduction is the process of electron gain. So we have considered 3 main aspects of oxidation and reduction definition. So another one in terms of electronegative element. I said that there are many reactions that involves oxygen and hydrogen. So we can easily define oxidation and reduction from that. But that doesn't mean we don't have some reactions that doesn't involve oxygen and hydrogen. So there are many of that. So example is this sodium reacting with chlorine, example this chlorine reacting with potassium bromide. So there are many examples of reactions that doesn't involve either oxygen or hydrogen. So if we don't know this definition now in terms of electronegative element, we may not be able to define our oxidation and reduction, because we get stuck if we stopped at hydrogen and oxygen definition of those are concepts. So now that will not take us to this new idea. It doesn't involve hydrogen or oxygen, rather it involves addition or displacement of electronegative element to or from reaction spacing. What are we trying to say? We have a sodium, it's a metal. We know that electropositive element. We have a chlorine, a non-metal, an electronegative element. So if we now add chlorine to sodium, what happens? It becomes sodium chloride. It is like we are adding oxygen to sodium, the same way we added oxygen to magnesium the other time. So what happens? Sodium oxidized in this case, like magnesium got oxidized the other case. So if sodium oxidized, this first reaction, then chlorine reduced. So the second reaction now, we have KBr here. If we remove this KBr from here and put Cl here, what has happened to the KBr? What has happened to Cl? Cl has been reduced also, because it has joined electropositive metal. Br has lost this electropositive metal to become Br, so it has oxidized. So in that case, I believe if we settle down to look at this and think about it, we should be able to have a new definition of oxidation now and reduction. So oxidation is the process of adding electronegative element to a substance, while reduction is the process of adding of removing electropositive element from a substance. Let me repeat myself. We have studied these reactions. we added electronegative element to sodium. We say sodium has been oxidized. Here, this as we have removed electronegative element from here to put here. Electronegative element has joined here. So what happens to chlorine here? What happens to chlorine here? What happens to sodium here? What happens to bromine here? So since sodium has been oxidized after chlorine has been added, KBr has been reduced after C has been oxidized, after Cl was added to it. Cl is a electronegative element. We say that oxidation is the process of adding electronegative element or removal of electropositive element. So if you want to treat electronegative element, just treat it like oxygen. In our first definition, treat it like oxygen. And you get the idea. So if you want to get electropositive element, treat it like hydrogen. So that now transfer the definition, now transfer it to this. Oxidation is process of adding oxygen. It is process of adding electronegative element. It is process of removing hydrogen. It is process of removing electropositive element. I think we are okay with that. So when you see oxidation, we want to define reduction. It is the directly opposite of what we have in oxidation. So now, to balance redox reactions, if we want to balance redox reaction, as I've said earlier, we need to know the electron transfer, and that is the second concept we'll talk about today. If you know this, the electron transfer, then we balance it in terms of atoms. We then balance it in terms of electrons and ions if they are not balanced before. So we need to do that. After doing that, we're cancelling out the electrons. So when we cancel out the electron, we know that which one transfer electron, which one gain the electron. So the knowledge of our electron transfer that we talk about in the second definition today or third definition today is going to help us doing that. So let's take reacting between sodium and chlorine as an example now. Sodium reacting with chlorine to form sodium chloride. So what really happened before reaction takes place? When we're talking about chemical bonding, we said before reaction can take place, the elements have to present themselves in a reactable way, as in a way that they can react. How would they do that? They have to transfer the electrons to become ions. If one element transfers the electron to the other one, the first one becomes ion, that is a positive ion, a cation. The second one becomes a negative ion, that is anion. So there is now going to be an attraction between the positive cation and the negative anion. In that case, another bond forms. That is what is called chemical bond. So let us now look at this now. If sodium wants to react with chlorine, since we know that sodium is a metal, easily loses electron. So it loses electron now to become sodium ion. In this case now, chlorine, for chlorine to be able to react, chlorine has to gain a lower electron. For information, the electron lost by sodium is what is gained by chlorine to become chloride. And we have established that losing electron is oxidation, gaining electron is reduction. So now we add both equations together. Then we look at if something is not balanced. If it's balanced, then we cancel out the electrons. So the most important thing is to make sure the number of electrons in those half equations, in each of them, equal. If let us assume that we have 3 here, we have 2 here, so we have to make them 6, 6, so as to be able to cancel them. In this case, we don't have to bother ourselves, since it is 2 electrons, we have 2 electrons here also. So we can just cut them, as I've done that. Then we have what what is here. So this is our sodium that got reacted, this is our chlorine that got reacted, and this is the sodium chloride. This is the sodium ion, this is chlorine ion. So when they now react together, they form sodium chloride. So 2 that is here is preserved. So we have here, this is what is here. That is not difficult. Another example is that second reaction that we talked about, chlorine and potassium bromide. In our potassium bromide, we have said that bromine got oxidized in that reaction in the first time that we talked about it. So how do we write the half equation? So we do it like the one we did now. The chlorine now, we do it the one we did now. So if there is imbalance of electron, as I said earlier, we try to balance it. If there is balance, then we proceed. We just add the two together, bromine and chlorine. Then we have the other one in the second half of the reaction, I mean the product side. So we now have this. So where we are having negative here is because of this chlorine and potassium that we are not considering here. So if we put that potassium here now, so it will neutralize this excess electron, so that we have balanced, we have a compound, not an ion. So our chlorine is balanced because nothing is clinging to it in the first place. So in the second reaction, in the product side, so this is our bromine now, this here, this is our chlorine now, this here. Another reason, the same reason that I said earlier, if you put that potassium here now, so it becomes a compound and not an anion. So what I've written now is not going to confuse you. I don't mean to confuse you with that. It is because we are not interested in the potassium that is here. What happens to potassium here happens to potassium here. So nothing has changed the potassium. That is why I didn't put potassium among the atoms or element that got oxidized or reduced in the first place. I mean in this place. I didn't put potassium here because it has lost electronegative element but has gained another one. So nothing really happened to it basically in terms of what we're discussing. So now, so if you like, you can put it. If you like, don't put it. It doesn't mean anything. So our own is just to get the oxidation half equation and the reduction half equation correctly. Balance them in terms of ion, balance them in terms of atom, balance them in terms of electron. Those are the three things. So if there is anyone that is not balanced, you have to balance them and make sure the number of electrons, in particular the number of electrons, are equal. Then you cancel them out. So before we go to the, let us have a quick recap of what we have talked about. We have defined oxidation and reduction in various ways. And the first way is in terms of oxygen and removal of hydrogen. Another one is the loss of electron, the addition of electronegative elements. So all those three now, if you want to define reduction, is the exactly opposite of oxidation. Addition of oxygen in oxidation means removal of oxygen, reduction. Addition of removal of hydrogen in oxidation means addition of hydrogen, that is number 2. Number 3, loss of electron in oxidation means gain of electron in reduction. Other one is addition of electronegative element or removal of electropositive element, that is oxidation. So reduction is going to be removal of electronegative element or addition of electropositive element. That is just what we are saying. So before we go today again, as usual, we need to get to exercise ourselves to be able to know if actually we have understood the little concept we have presented. So in which of the following reactions does reductions take place? So if you are still confused about reduction, just go back to our definition of reduction. Gain of electron. So just look at it and you see that this is the answer. The reaction that takes place in a Daniel set is dash. This actually involves transfer of knowledge from physics to chemistry. it is in physics that we talk about Daniel's cell. So I just brought the question because I think you should have been taught these electrochemical cells in physics by now. So look at what is happening in Daniel's cell, then you now add it to or transfer it to this, because in Daniel's cell you have ammonium chloride, you have H2SO4 and that. So if you look at that, you are going to see that is option D. Electron is being lost because it is actually the metal that is inside that is losing the electron. That electron that is being lost is being gained by another metal. Another metal that is gaining, that is why that makes the cell to discharge. Because if cell is working, that means the metal is losing the electron. Then if the electrons being lost are not being gained, there's going to be a reservoir of electron and the cell will be damaged because of polarization. So to forestall that polarization, that is why another compound is there, another element is there to gain those electrons. So then the battery, instead of being damaged, is got discharged. Thank you very much for listening. Don't forget to share and like our video. So next time we are still continuing on this topic. Thank you very much.